Hello students, let's discuss about molecular orbital theory. I am Dr. Mitali Pal, Assistant Professor in the Department of Chemistry, USDM. This is a very important topic in the inorganic chemistry. Okay, so let us start. So what is molecular orbital theory? This is often abbreviated as MOT as well. So this is actually a theory on chemical bonding in molecules, right? Who have developed this theory? Hunt and Mulligan in 1932, they have developed this molecular orbital theory to describe the structure and properties of different molecules. Okay, now, as we are talking about molecular orbital theory, it deals about molecules. So, how molecules form? We know that two or more atoms, when they combine, they form molecule. Now, when they combine, what happens? Bond forms between the atoms. It can be covalent, ionic, or other type of bonds. Now, in general, according to valence bond theory, what we know that if this kind of two atoms with electrons comes closer and their orbitals overlap, their electrons are shared by both, and then this way a covalent bond formation happens, right? So this is the general theory how molecules forms, we all know. Now, after when molecule is forming, obviously molecular orbital will form. First, electrons resides in the atomic orbitals. We know all these things. Now, when molecule is forms, electrons will reside in the molecular orbitals. Okay. Therefore, it is very important how to understand how molecular orbitals form. Okay. Now, atomic orbitals actually combine to form molecular orbitals. Okay, so atomic orbitals, how they looks like, depending on that, the molecular orbital will have that kind of shape or energy. Okay, so here a few examples I have shown in this slide. You can see that 2s, that is sphere shape, and 2s of, so two atoms, let's say 2s of one atom and 2s of another atom, when they combine, see here they are in the same phase, when they combine they form sigma molecular orbital with this phase. Okay, and it will look like this. When 2pz or 2pz orbital overlap head-on in the z-axis, on the z-axis, their head-on overlap happens because they are in the same phase. So sigma molecular orbital forms, and the shape of the molecular orbital will look like this. The shape of the molecular orbital will depend on the shape of the atomic orbitals. Now, when they have side-on overlap to form pi molecular orbital, so they will overlap and this will be formed. Similarly, for 2py also. So, the atomic orbitals, they combine or mix, overlap with each other to form molecular orbitals. Okay. Now, some of the conditions is there so that two atomic orbitals can mix. They have to fulfill some of the criteria. What are those criteria? So these are very important criteria. First one, the atomic orbitals should have similar or same energy levels. Okay, so this is described more detail by showing this molecular orbital diagram. You can see that energy increases in the upwards, and let's say atom A and atom B is making a molecule. Atom A are having atomic orbitals 1s, 2s, 2p. Similarly, B is also having those orbitals, and they are placed energy wise. So the lowest energy will come in the lowest position, then accordingly with increasing energy the orbitals will be placed. Okay, now this 1s orbital of atom A and the 1s orbital of atom B, they are having same energy. So they are fulfilling these criteria. That's why these two orbitals can overlap and form a molecular orbital bonding and as well as anti-bonding molecular orbital. So I'll also discuss then when molecular orbital theory case anti-bonding molecular orbital also forms. But in this point, you understand that 1s and 2p, these two orbitals are having lot of energy difference. So there is not possible of overlapping 1s and 2p orbital. They cannot overlap and make a molecular orbital. Okay, 2p can overlap and make 2s and okay, like this. So they should, the atomic orbitals, combining atomic orbitals should have similar or same energy levels. So this is a very important point. What is the number 2 criteria? The atomic orbitals which are taking part to make a molecular orbital, they should have same symmetry about the molecular axis. Normally Z axis is the molecular axis, means the sigma bond is forming on the Z axis. How sigma bond forms? By head-on overlap. Okay, so how, please understand this point with this example. Here, one 2pz orbital of one atom and the 2pz orbital of another atom is given in the along the z-axis, and they are in the same phase, so they can overlap and they can make a sigma bond, molecular orbital. Okay. Now, for 2px, in as the molecular axis is z-axis, so 2px will be perpendicular to the 2pz. So in this direction, and they can have side-on overlap to make a pi molecular orbital. So you see the 2pz orbitals do not have any electron density in the x-axis, right? That is node in the x-axis. Similarly, the 2px orbitals, they don't have electron density in the z-axis. So there is a node along the z-axis, right? Therefore, if you try to overlap one 2pz orbital and another 2px orbital, although they are having same energy level, because it is also 2p, this is also 2p, but they cannot overlap. This overlap is not possible because in 2px orbital have no electron density in the z-axis, although 2pz is having, but there will be no overlap possible. And for 2pz, there is no electron density in the x-axis, although 2px is having, but there will be no possible overlap. So that means 2pz and 2px having different axes of symmetry. Their symmetry is not matching. Therefore, they cannot overlap and form a molecular orbital. So this is this point means. Okay. Now, you just see the third point, that the molecules should be close enough, the atoms. Okay, if the atoms cannot come very close to each other, then this overlap is not at all possible, because first they have to come closer, then only the bonding is possible. So that is a very basic thing. Okay, now let us go to the next slide. Now, how mathematically how we can represent a molecular orbital? All of you know about the Schrodinger equation, which you have already read before. What is Schrodinger equation? You know this is a very important equation. Why? Because the solution of the Schrodinger equation gives us a wave function which is represented as psi. So what is wave function? You know that electrons are having particle and wave nature both. So when electron is having this wave nature and it is having some behavior, it is moving in the space. So to determine the behavior of the electron in a space will give you the atomic orbital. What is atomic orbital? This is actually how electron behaves in the space, how it is occupying the space. Okay, that picture is actually atomic orbital, and that is given by psi, the wave function. Okay, you please try to revise all these things. Okay, this is a very important equation. So Schrodinger solution of the Schrodinger equation gives us the concept of wave function, and wave function is what? It is actually the atomic orbital where electron resides. Wave function is atomic orbital where electron resides, and its behavior actually represents electron, and its behavior represents atomic orbital, and mathematically it is a solution from the Schrodinger equation. So all of you already read about these things. So each atomic orbital will have a wave function associated with it. Now when we combine the atomic orbitals, they can be added or subtracted from each other, and then we'll get the molecular orbitals. So molecular orbital is termed as, this process is termed as linear combination of atomic orbitals, in short LCAO, when we add or subtract the atomic orbitals to get the molecular orbitals. So let us see more details on these in the next slide. Here you can see the molecular orbital is also represented as a wave function, capital psi, and it is a product, it is a linear combination of two atomic orbitals. Let's say this is one atomic orbital, 1s, right, and the associated wave function is psi a, and this is another atomic orbital, 1s, and the associated wave function is psi b. So psi A and psi B can combine, we can add them up to get the molecular orbital. When we add them up, then we get the bonding molecular orbital, and when we subtract them, we get the antibonding molecular orbital. Now here, what is Ca and Cb? So these are the coefficients which quantify the contribution of each wave function to the molecular wave function, atomic wave function to molecular wave function. What that means? So when a molecular orbital is forming, this atomic orbital and these atomic orbitals can have same contribution or may have different contribution of its orbital to form the molecular orbital. When they have same quantity, same amount of their contribution, then it will be 1 1. When they have different, so it will come different values. They may have different contribution also. Psi A may be giving more of it, or psi B giving less, or they can give, say, they can share equal amount to form the molecular orbital. So this is the this is to quantify the contribution of the atomic orbitals, which is making the molecular orbital. Okay, so I hope you are clear about LCAO method, linear combination of atomic orbitals, which giving us the wave function of the molecular orbitals. Okay, now let us go to the next slide, where we'll see that when the atomic orbitals are added and when they are subtracted. By adding, which kind of molecular orbital forms, and by subtracting, which kind of molecular orbitals forms. Now as you understood that orbitals are actually wave function, orbitals are wave functions, right? So wave functions will have wave-like behavior. So when the wave function of one atom and the wave function of another atom are in the same phase, so this picture shows us in the same phase. You see, these are in the same, exactly same, they will overlap exactly same way, right? If we overlap one orbital with another one, so there this thing is matching, and their amplitude, that's why will increase, because their phase is matching. So if this is plus, this is also plus. As their phase is matching, the amplitude of the wave will increase, and therefore it will increase the electron density, and it will form a bonding molecular orbital, and this is called as constructive interference. But when the two atomic orbitals are in the different phase, okay, one is plus and one is minus. You see the picture of the wave function, how they are in the different phase. You can see it is having phase plus minus, and this is having minus plus in the same position. So when you overlap one atomic orbital with another one, you see there will be no, they will cancel each other. The amplitudes will cancel each other. So therefore there will be formation of node. There will be no electron density, right? There will be no electron density. So one node will form. Node means there is no electron density. So one node will form between these two. Okay, and you can see this will be called as anti-bonding molecular orbital, and it is psi a minus psi b. Okay, I hope you understood when bonding molecular orbital and when anti-bonding molecular orbital is forming. When they are overlapping in the same phase, then it is bonding, and when they are overlapping in a different phase, so it is destructive interference between the waves. So then anti-bonding molecular orbital will form. So we will see how the orbitals will look like when they are overlapping in same phase or different phase. So these pictures already you have seen when they are in the same phase, how the molecular orbitals are looking. So when they are in the different phase, anti-bonding will form. So you see 2s and 2s, these two are in different color, means they are in the different phase. If one is plus, another will be minus. So there will be node formation between these two. So the sigma anti-bonding molecular orbital will form, and it will look like this. Similarly, pz, they are having different phase. So anti-bonding will form. So similarly, pi anti-bonding molecular orbital will form when side-on overlap is there, but they are in the different phase. Similarly, for 2py also you can see the antibonding in forming. Okay, so till now what we understood is atomic orbitals combine to form molecular orbitals. So for combining atomic orbitals, there are three conditions, three criteria, what they should match, then only the overlap is possible to form a molecular orbital. One is they should be close enough, another is their energy should be similar or same, their symmetry should match. Okay, these three criteria is there. And then we understood that what is actually molecular orbital? It is wave function, because atomic orbitals are also wave function. So by adding or subtracting the wave functions, we get the wave function of molecular orbitals. And when we add up, then we get bonding molecular orbital, and the wave functions, when they are having destructive interference, they will form anti-bonding molecular orbitals. So I hope you understood till now what we are trying to figure out. Okay, so let us go to the next slide, where the differences between bonding molecular orbital and antibonding molecular orbital of molecule is given, which we have already discussed. Just for summary, you see that bonding molecular orbitals are formed by addition overlap of atomic orbitals, and antibonding molecular orbitals are formed by subtraction overlap of atomic orbitals, right? And we can represent it as like psi equals to psi a plus psi b for bonding MO, and for antibonding it is given like psi star, psi asterisk. It is psi a minus psi b. So bonding molecular orbital will form when lobes of atomic orbitals have same sign, and there will be a constructive overlap. And when antibonding will form when lobes of the atomic orbitals have different signs and they have destructive overlap. And you see, bonding molecular orbital always have lower energy and antibonding than the energy of the atomic orbitals. Okay, and the antibonding molecular orbitals will have higher energy than that of atomic orbitals. We can see from this. Okay, so let us summarize what we have understood till now. So what are the key features of molecular orbital theory? The total number of atomic orbitals will be equal to the total number of molecular orbitals. Okay, if 2 atomic orbital is combining, 2 molecular orbitals will form. If 4 is combining, 4 will form. Okay, so as simple as it is. And bonding molecular orbitals have lower energy, antibonding molecular orbitals have higher energy. Electrons, now after forming the molecular orbitals, electrons in the molecule will be filled up in the molecular orbitals. Before formation of molecules, the electrons resided in the atomic orbitals. Now electrons will be filled up in the molecular orbitals after a molecule is formed. Then what should be followed? The electrons will go lowest energy molecular orbital first, and then next higher energy orbitals will be filled up. And for effective formation of molecular orbitals, the atomic orbitals should have similar energies that we have already discussed. If they are exactly same energy, the molecular orbitals will have very effective overlap, and it will have most effective formation of molecular orbitals will occur. If they have different energy, then it will be not so effective. And wave functions of molecular orbitals are obtained by how? LCAO method, that is linear combination of atomic orbitals. Another thing, that shape and size of the molecular orbitals are determined by the shapes and sizes of atomic orbitals. So we have seen how atomic orbitals are combined to give molecular orbitals, and the shapes, how it is changing. Okay, so depending on the atomic orbital's shape and size, the molecular orbital will have that kind of shape or size. And when electrons are filled up, all the 3 principles which we follow when electrons are filled up in atomic orbitals, it is above principle, Hund's rule, and Pauli's exclusion principle. So all these 3 principles will be followed. So already above principle is about what? The electrons goes to lowest energy orbital first, then to higher energy orbitals. So already we have discussed this one, that electrons will follow first fill up in the lowest energy orbital, molecular orbital, similarly, and then higher energy. Then Hund's rule is what? Hund's rule, it is that first, if you have same energy level, more than 1 orbitals, then electrons first fill up 1 means singly occupied, and if all the orbitals are singly occupied, there are no vacant orbitals, then only electrons start pairing up, not before than that. So this is also followed in the when we fill up electron in the atomic orbitals. So this is the Hund's rule. It should also be followed here. And Pauli exclusion principle, what is that? So in one molecular orbital, 2 electrons cannot have same spin. They should have the opposite spin. That is Pauli exclusion principle. So all these 3 principles will be also followed for a molecular orbital filling up electrons. Okay, right? So I hope you understood the main features of molecular orbital theory. So here what we have already discussed, you can see here. This is a diagram, molecular orbital diagram of hydrogen molecule, the simplest one, which is having only 1s orbital. So molecular orbital which is bonding, it is lower in energy level, and antibonding molecular orbital is having higher energy. And one is having 1 electron, this one is having 1 electron, and then both electron will be, because here 1 molecular orbital will form, so in 1 energy level 1 molecular orbital is there, so both the electron will fill up here, so no electron will go the higher energy. So we can see the bonding molecular orbital is having lower energy than the atomic orbitals, and the antibonding molecular orbital is having higher energy than the atomic orbitals, right? So these things are now clear to us. Okay, so this we have already seen. Okay, so I am for today's lecture I finish here. So from the next lecture we'll start from here. Okay, so I hope you understood the first lecture on molecular orbital theory.